So visual binaries are systems where the two objects are spatially resolved. And as a function of time, you can see the objects moving around their common center of mass. Kruger 60 is an example of a very nice visual binary. Now let's come to measuring the parameters using Kepler's laws, a kind of a modified version of Kepler's laws. The modification exists because Kepler gave the laws for planets and the sun. And the mass of the planet was actually negligible compared to the mass of the star. But please understand that Kepler's laws can be derived from the basic principles of Newtonian mechanics. One principle is that the centrifugal force is caused by gravity. And it is that particular force which gives Kepler's third law. So we have seen that for two-body dynamics, Kepler's laws actually can be derived from Newton's laws of motion. And here, when we are talking about a binary system of stars, this is a modified version of Kepler's laws because in Kepler's laws, the mass of the planet is negligible compared to the mass of the sun. Here, we are talking about two masses which cannot be neglected. This quantity, a cube upon p squared, can be termed as the mass function of the system. And whenever you have a visual binary and you can measure A and P separately and individually, then you can obtain the mass function, and that is the first thing that you normally measure for a binary star system. And following the mathematics that we have developed before, you can see that you can then obtain the distances of the individual objects from the center of mass. Now, here we can see the circular orbit of a system consisting of two masses which are exactly the same. So what happens out here is that both the objects are on the same circular orbit, same radius from the center of mass. The center of mass is the center point of the line joining the two masses, and they are always diametrically opposite to each other. Then, when we talk about two masses which are different, then you see that although they are moving around in a circular orbit, rather in their own respective circular orbits, but the radii of the orbits are not the same. The radii is defined by the distance from the center of mass to that object. And obviously, you can see from the definition of center of mass that the heavier object is closer to the center of mass, and hence the radius is smaller. And the lighter object is moving around with a distance that is greater than the heavier object. Then, when it comes to a greater disparity in the masses of the two objects, this can represent a very heavy mass star and a small mass star, or you can use the same mathematics to describe the Earth-Moon system. Here, what happens, the center of mass is actually moving inside the body of the heavier mass, and hence you can see that the heavier mass is moving around a point which is inside the body. And as an extreme case, when you have the two masses very drastically different from each other, this can represent a stellar mass system also when you have a very heavy mass star and a very light mass star, the K-type or M-type stars. So in that case, what happens? The bigger object is moving around the center of mass, which is very near to the center of mass of its own individual body. And hence, what you see is kind of a wobble. This system is again very similar to the Earth-Sun system, or rather Sun and most other planets. So, this is how we we can visualize the circular orbits of a two-body system. Okay. Now, here are some examples of visual binaries. So, you have this image of Sirius. This is Sirius A, and this is Sirius B. And Sirius B, okay, has a very, very interesting history. Okay, so basically, it was known as the dog star, and Sirius B was known as the pup because it's a very, very small object following the bigger object. Okay, and here you can see that Sirius A is the second brightest object in the sky as measured by the eye from Earth or any other instrument from Earth. Sirius B is a very faint object compared to Sirius A, and this happens to be a white dwarf star. You will know white dwarf star, what a white dwarf star is, if you know the evolution of stars, which has a mass similar to the sun's mass. It is the end product, but this knowledge was gained only in last 100 years. Before that, we didn't know what is the nature of the white dwarf stars and how they were created. But people realize that they have a huge amount of luminosity compared to the physical size. And that is why they were known as dwarf stars. Okay, white dwarf stars. Now, this is an X-ray image of Sirius A and Sirius B. And you see the amount of light that you receive in X-rays is just the opposite of what you see in the optical regime. And this tells you that it is the physical processes that determine how much light I am receiving in a particular wavelength band. The physical process that gives rise to the optical emission and the physical process that gives rise to the X-ray emission may be the same, may not be the same. Okay, you should go back to your thermodynamics and then ask the question and understand why is it that Sirius B appears brighter in X-ray, whereas it appears so faint in the optical. So now, Sirius A is actually negligible in X-rays, which is actually very similar to all the stars that we see. Most of the stars in the normal lifetime has very negligible X-rays. And what you see out here, it is appearing very bright in X-rays compared to other stars of similar mass. And that is happening because of a huge amount of ultraviolet radiation is getting reflected by Sirius A, and the origin of the ultraviolet radiation is Sirius B. Okay, so the reflection effect is actually enhancing the X-ray luminosity of Sirius A. Normally, in X-rays, Sirius A should be more dim, less bright.